retaining wall design, you can just add up that the dynamic component. Then all other design procedures should be the same. So now you can claim that you know how to design retaining walls for dynamic loading, as far as you know the acceleration from the earthquake. Okay. Then how do we actually know the earthquake acceleration? Okay. Huh?
Measure it.
You can measure it, but many times the measured earthquake vibration is not really, may not be really designed earthquake. Okay. So what I will say is this one. You can knock the Dr. Mullen's door and ask him, okay, what is the earthquake design acceleration of the earthquake in Oxford area? I mean, depends on which area you are in, design acceleration will be different. I recall the design acceleration for earthquake in somewhere in here should be 0.170 or somewhere around there. In California, it may be high. Okay? And today, we will talk about, what should be the lesson number? 21. Dynamic slope stability. The concept is very similar to the previous dynamic oscillation theory. Objectives is going. We know the dynamic conditions. That include earthquake, cause more critical conditions on the slope. And we need to know how to incorporate dynamic effect and incorporate dynamic effect into slope stability problem. Okay. Ice maker. I don't know. Okay. Caution first. Okay. The technique that we are going to talk in today's class is classical approach. Classical approach, I mean, this approach is correct, it's reasonable, you can use it if you want, but many times nowadays people try to use some kind of dedicated software to design, to analyze dynamic slope stability. Okay. Dedicated software means, okay, we know that slope stability calculation is very complicated. Typically we use the ordinary method of slices. It requires long calculation time, and we usually use the dedicated software. Same thing for the dynamic slope stability problems. Okay. I will talk about how we can incorporate it conceptually. If you want, you can do the hand calculation, but again, in real life, we incorporate this concept into a dedicated software. So many times, you may even do not know whether you are incorporating, how you are incorporating the dynamic effect. But again, in the background of the software, it has similar concept in there. Okay? Consulting companies. Usually use dedicated software. Okay. Those softwares will typically lead to additional input, so-called horizontal acceleration. It will require typical input like the cohesion, internal friction angle, thickness of the layers, height and slope of the slope, but it will require additional one. And time to time, okay, it requires design waveform. Design waveform means, okay, whenever we got to design something that may reflect our earthquake vibration, or maybe some machine vibration, usually there are two ways to incorporate those dynamic effects. First one is make everything very simple and just use the acceleration. Something like when we have earthquake record, we know how to convert it to the equivalent number of cycles with certain acceleration. That is a simplified technique. And another technique is we just input the waveform as is. Okay? And the built-in software will track down the waveform. If it want to compute the acceleration, then it will compute it. That kind of the calculation procedure is already built in the software. Or time to time, the logic in the software itself, it will utilize the waveform as is, without computing the average acceleration or whatever. Okay. So anyway, for the typical dynamic slope stability analysis, either this one or this one will be your additional input parameters. Okay. Probably it's better to go to the other side. This approach is usually called pseudo static approach. Time to time, this is also called the pseudo-dynamic approach because it's not really static, it's not really dynamic. Okay? The concept is this. Okay. We will add horizontal force, horizontal dynamic force, ORC, and follow a similar procedure to static slope stability analysis. I guess this approach is actually easy to understand because we already know how to analyze the static slope stability. And I will plot a small slope. Let's say this one is a slope, surface, bottom surface. And at this moment, to make it easy, I will assume it will have circular failure with center of rotation somewhere here. We assumed circular failure. Again, the only reason why I assume circular failure is because it's the simplest form. Okay? And maybe I will correct the point a little bit so that it's easy to derive the equation somewhere here. Okay. Is it about? The figure is not very accurate, but we will say our center of rotation is here. And this distance, we will say radius of rotation. And driving force will be actually caused by the weight of this one. We will say weight is W. And when there is the rotational motion, okay, and there will be the resisting stress from the soil. Okay. And this weight will have rotational radius or arm length. This one will be the arm length. We will say this one is L1. Okay, L1. Now what I will do is, okay, I will add dynamic acceleration to this soil weight. Okay. I will add some kind of, please look at this one, horizontal acceleration to this one, this way acceleration, not this way acceleration, because this way acceleration will make the higher driving force. So I will say along this way. Okay. So H times W, by the way, this K sub H is horizontal acceleration divided by gravity. The same concept to the previous one. Okay, then, in general, we can define factor of safety should be M, resisting moment, divided by M, driving moment. So far we use exactly the same definition as in the static slope stability problem. And M, resisting moment will be, think about what will be the resisting moment from this shearing resistance. Okay. Moment is force times arm length. this is a stress, so force is this stress times area on this surface. How can you get the area?
Surface area of the circle.
Surface, let's say this length is, let's say this is, this point is A, was B. Anyway, in my note it says this point is C. Then surface area is arc length times unit width. So I would say there is tau times arc length AC times 1 is the shearing force times, I would say this arm length is L2. Then it should be this one times L2. I will just rewrite it in this way, tau AC L2. That's the resisting moment. Then let's think about the driving moment. Wait a minute. What am I doing? Something is wrong in here. What is wrong?
You don't have the need to L2.
Arm length is not L2. Arm length should be R. Okay. Okay. Then driving moment.
Oh, somebody's got to sing.
That didn't ring there.
Oh, I thought it was Papa's song.
Mine is off.
God. Papa's song and sing again.
I don't know whose jacket that is.
So this guy is guilty?
Yeah, whoever jacket that is.
Is that your jacket, Dr. Song?
No. It's not your jacket?
No.
Maybe that guy is trying to find out where is his jacket. We try to find out his jacket and let him know. No. How can we let him know about it if his cell phone is here?
Whose is it?
Call a friend on the cell phone.
Yeah. Anyway.
I don't know. We'll find out later.
Okay. When driving, you are the one who calls this one? Okay. When driving should be, look at this one, this W times, okay, this is driving force, this W times
L2. Or no, L1.
L1 plus this one times
L2.
L2. Got it? Okay. That is W times L1 plus W KHW times L2. Okay, then we can say factor of safety for dynamic condition should be resisting tau R length times R divided by WL1 plus KH WL2. Okay, in the simplest form, we have dynamic effect right here. Okay. We have dynamic effect right there.
What's tau AC times?
R
AC's arc length.
AC is the arc length.
Yeah,
so-
yeah, arc length. Yeah, but what's the?
Where'd the one come
Is that
from?
one?
Unit width.
Oh, this one, the unit width.
Oh, okay.
Usually, there are many articles just omit one and you may not have any clue, but they omit it because it's 1. Actually, in the soil mechanics foundation engineering, I found out that if I don't explain it this way, usually students are lost. Okay. Now you understood where we can include dynamic effect. It will go into the driving force. Any questions? So surely when we have some vibration, some horizontal acceleration, our factor of safety will be, it will become lower. That means the slope may be okay during the regular season, but when it's the time we have the some vibration, then the slope may fail. Okay. And many times, actually, there is the additional factor for special soils like the liquefiable sandy soils. When we have some vibration, our shear strength will become substantially lower. Then this guy will become even lower, right?
So you can't design for dynamic conditions? Because, well, I mean, it seems like, I don't know what I'm trying to say here.
You are right. I mean, if we know how much strength reduction we have, we can include it in there. Yes.
Do you not include the vertical component?
Okay, that is actually the question that I was waiting for. Okay. In the previous class, we tried to include horizontal component and vertical component. This time, vertical component was not included. Okay. Why?
Because we weren't trying to see what the failure was last time.
Hmm?
I mean, were we not trying to see what the failure was last time, or this time we don't? This time, last time we had the KH or the horizontal component going the other way.
The KH can go always both ways, this way and this way. But when it goes this way, it's more critical. That's the reason why we include it that way. In real life, the K, you may say K, T times W should be there, and there will be the additional moment. But it's not always true. Not always true, I mean. We know that the location of the resultant force for the dynamic force is not necessarily the same as the point of the static one. So let's think about, let's say, that the dynamic vertical force is acting on somewhere here. Okay. Then arm length is not really substantial, right? Arm length is not substantial, or maybe this arm length times 0.2 times this weight may not be really substantial. That is the reason why typically we don't include it in here, because that effect is there, but that effect may not be really substantial.
So what if, what if it was a case where it was acting farther towards, or on the other side?
Then you have to include it.
How would you go about measuring what location the vertical?
We don't know.
No idea.
We don't know. Okay, and actually the if you can find out where your dynamic vertical force is acting, it may be better to include it in here. But this approach is not my own equation. That is usually equation that is usually used. So my guess is people thought about those vertical acceleration effect, and I would say by some empiricism or whatever, they figured out that vertical component may not be usually substantial. But anyway, anyhow, this one is the simplest condition. Now I will introduce a little bit more realistic conditions.
What about the shear strength though? I mean, as you said, is that the shear strength of the soil before the dynamic?
Before the dynamic condition, before the dynamic loading. But again, I will talk about a little bit more realistic condition in the next topic here. Just some additional comment. In here, this acceleration a sub h should not, okay, it's not the peak acceleration. Because usually earthquake vibration causes several different cycles, and this one should be the average one.
So that's like the 0.65.
Yeah. Okay, the whole region is okay. Big amplitude may cause some big impact, but even lower amplitude can cause additional damages. So we usually use the average acceleration. Okay. Then in the soil mechanics, we also talked about Oxford Middle School technique, ordinary method of slices. This is the center of rotation. Let's think about only one slice. We will say this is slice N. Okay. And weight of this slice is Wn, and along the horizontal direction there may be horizontal acceleration, so I will say kh times Wn, and at the bottom there will be the frictional resistance. This time the force will be expressed as T resistance, and there will be normal force. I would say this normal force is N R. And this angle, inclination angle, I would say alpha N. Okay. Then we will try to compute TR, resisting force, can be, okay, I will write down the expression first, then I will explain it. CVN secant alpha N plus force C is the cohesion. B is the length of this section. Length of this one.
The arc length?
Arc length. Many times that arc length is almost the same as the straight line length because we cut it into many small pieces.
And then alpha n is the angle.
Alpha is the this inclination angle. In this line, if you assume from here to there, there is a straight line, it has the inclination angle. Secant and this secant is there because of just trigonometry. This BN, no, I'm sorry, this BN, this is not BN, actually this is the BN. It really does not matter. If this is the BN, then this secant alpha n will not be there. Okay? Because this is the BN, secant alpha is there to show this length.
So it's just the width of the slice.
Yeah, anyway, this one, the slice, I would say slice. How do you call this one? This is not really width. Slice arc length. Okay. That's the resisting force. And we will try to obtain the resisting moment. Resisting moment will be really what? We have many different slices, so I will say summation of TR times radius. Okay? And I will just plug in this TR in here. R is always constant, so I will say there is summation dn secant alpha n plus nr tangent phi. Then we will compute driving moment. Driving moment let's say driving moment should be summation of driving moment of all those different slices, Wn times this distance plus kh Wn times this distance. That should be the driving moment, right? So I would say Wn times to make it general, I would say L1 plus KH Wn times L2. Okay. L1 is this distance, L2 is that distance. This L1 and L2 should be obtained from trigonometry, or if you plot geometry of this one in scale, you can just pick up this number and this number. Okay. So I would say we can define those two from 3. What you will find is actually that L1 and L2 can be expressed sine alpha n plus k sub h w n times L2. That L2 may not be expressed in terms of sine and cosines, but L1 is r sine alpha n. You don't feel comfortable with this expression? Let's see whether that is similar to the this expression. There should be this distance, right? And let's plot a line from here. This alpha looks like very similar to this one and this one, alpha n. If this is r, then this is alpha n. Yeah, it looks like this L1 is really r sine alpha n.
Is L1 to this middle of that?
From here to middle of the this slice.
Would that not be cos?
I think it's sine. Always sine, cosine, tangent.
What's the known length there?
R.
Yes, so that's
Which one?
that length right.
This one? This
the
one?
one below that one.
This
that
one?
length. That's the known length.
This one is R, but from here to there, we don't know it at this moment. If we know this one, we can find out this length. But we don't, this length is not really needed. We need to know this one. Because
Right.
that is the arm length.
Right.
But we know this one is the radius, R. We know this angle is this one.
Mm-hmm.
Let's plot it this way. Okay. We know this is R, this is alpha n. Sine is this one. Okay. Whenever there is confusion, always try to record it this way. Sine, cosine, tangent. This is my way of recording those things. So this one is sine.
But that, yeah. So if you do sine of alpha, that's going to give you the length, the vertical length. I thought we were looking for the horizontal length.
Yeah, yeah.
So cosine.
Okay. You agree that this one is sine, right?
Mhm.
Then let's rotate it 90 degree.
Right angles at the top.
Okay. Then flip it. Okay. We are still talking about this guy, right? It's still sine.
Mm-hmm.
Then flip it 180 degree this way. Then it will be this shape, right?
Right angle is.
Uh-huh.
Give it out. I'll figure.
Okay. It's not really difficult one, but looks like you are confused. If typically when somebody is confused for this one,
It's not, I'm not confused with the sine and cosine. I mean, I understood it. I guess I was just confused as to what distance we were looking for.
maybe I will correct this figure a little bit so that it may be easier to understand. So look at the big triangle. Think about this one.
Oh, okay. I see now. Yeah, I was looking at
This one?
I was looking at that little one and saying,
Yeah.
okay, that'll give you, the sign of that'll give you that little vertical. I see it now.
Yeah.
You need that vertical, I got it.
Yeah. I mean, after you figured out this one, then you can find out this one, but we don't need to know this length.
Yeah, I was just looking
Okay.
at the wrong one.
Okay. Then I will finalize our expression. Factor of safety for dynamic condition is resisting divided by driving that is the factor of safety for dynamic conditions. Of course, for this one, if you want to include vertical acceleration, you can include it. But typically what happens is, based on my experience, even though we include the vertical acceleration, the difference in factor of safety is not really substantial, usually less than 0.1. Then maybe the reason why people just ignore it.
And what's the fee? Is that the
Oh,
contingent fee?
internal friction
Yeah,
index.
okay, I was just making sure that's what that was.
So I guess you guys understood the overall logic is we just include horizontal acceleration somewhere in the driving force equation. Then that should be it. Okay.
You sound like you need some Beano back there. Corey's got a big gas this morning.
Some comments. Okay, we already talked about that, but this one is just one more repetition. Okay. Case of H. Okay. Again, case of H has positive component and negative component. Okay, because it's vibrating this way, right? If one is positive, one is negative. It should be always positive in your input because that condition is more critical. And when you use some software, okay, it requires your definition of coordinate system. Okay. In some software, okay, you need to coordinate system. Then means let's say you define the coordinate system plus x, this is plus y, traditional Cartesian coordinate. Okay, then the acceleration that you got to use is this one, right? This one should be your AH, and it should be input as the positive number. But time to time, especially for the beginning engineers, time to time they may do the really weird things. Let's say you define your coordinate system. And you may define your slopes in this way. Okay, if you define your acceleration this way, because I said it should be positive, then this positive is wrong positive, right? In that case, you got to put acceleration along this way, and this can be negative. Always think about the critical condition. I know the software name is stable. You can define your slope this way or this way, and you got to be just watch out the symbol. Probably, I guess you guys are ready for the homework. Slope angle is 30 degrees. Gamma is 17 kilonewton per cubic meters. Cohesion is 10 kilonewton per meter squared. Phi is 30 degrees. KH is 0.2. Okay. And you got to compute factor of safety for static condition and factor of safety for dynamic condition. Okay. And you need to assume water table is at the surface. That means you got to consider water table. Okay. You have two options. You can use the hand calculation using the one of those formula, or you may just download some free slope stability software. You can use the slope stability software. My recommendation is try to download some of those free slope stability software. They are just available in the web. Then just you can put the shape of the slope and show the location of the water table. Plug in those numbers and you should be able to obtain this one and this one. Yes.
If you were to do this by hand,
Hmm?
or not necessarily by hand, but say you were to use some kind of numerical solver like MATLAB or something, what would be a good assumption as far as number of slices?
Okay, usually less than 10 should be good enough.
Less than-
You don't, if you want, you may use the 100 different slices, 1,000 different slices, but usually less than 10, somewhere 6 or 7 slices will give us enough accurate number.
So we could do it that way too.
Yeah.
Just look-
It's okay to follow the that way.
Because you could do it. You could just type the equation in one time
Mhm.
and then loop it 6 or 7 different times. And
Yeah, you can just find out the line that shows the minimum factor of safety. You know that when you do the calculation, it's not one-time calculation. Initially you will assume your center of rotation is somewhere here. Then you compute the factor of safety. Let's say this is 1.5. It's not going to fail at 1.5. Then assume some other point. Compute the factor of safety again. Usually, probably you may want to do the 100 different calculations for 100 different center point. And the line that has lowest factor of safety will be the possible or future or potential failure line, right?
Why
So
can't you set in your factor of safety then?
Huh?
Why can't you set your factor of safety to where it will fail and then back salt to get to the arm?
It's really the same thing. Okay. Actually, the flag, the one that Sudi is using, is the software that is working in that way. And all other softwares just find out all different factor of safeties for different projected failure lines. Don't forget that water table is at the subject.
It's a guitar.
Good talk.
I mean, close.
Oh,
yeah.
I have better talk from now on.
No, we need to find the person whose coat that belongs to. We need to go search for him out there.
It could be at the union.
Yeah.
They could be getting food right
It could be in your room.
It could be the chancellor's. We need to go check with him and see if it's his jacket.
The chancellor really is not expecting you guys because he knows you guys will be in the class, right?
No,
You don't even
yes,
know our
yes.
names.
Then, okay, let me talk about the a little bit different slope stability problems that we will talk in the next class. And another big, or maybe the really critical geotechnical structures that is very sensitive to the dynamic effect is the dam slopes. If dam fails, then we have the big property loss and a lot of the life losses too. So in the next class, we will talk about the it's essentially slope stability problems, but because of the dam is the very unique structure, the approach is a little bit, I would say, it's different, but that is also a little bit advanced. We will consider several different factors for dams.
What factor of safety do they design them to?
For what, this kind of slope?
Dams or?
Oh, okay. That is real good question. Usually let's say if we just pick up one factor of safety for general slopes, I would say somewhere 1.2 or 1.3.
So they don't base it on affected area if the dam breaks?
If we just pick one factor of safety for whatever slopes, usually there is somewhere 1.2 to 1.3. But let's say this dam is a really important one. Then probably you may want to increase the factor of safety a little bit higher, 1.5. Right. Also, you also need to consider some other factors like let's say you did not consider dynamic effect. Then probably you'd better apply a little bit higher factor of safety. But in another case, yes, okay, you consider the dynamic effect, then you don't have to use the same factor of safety like 1.5. You may say, okay, I consider the dynamic effect. This one should be the most critical condition. It's already considered. So I will say the required factor of safety for this slope is 1.1 because I consider the dynamic effect. So
I'm sorry.
Go ahead.
So like when say you're actually designing a dam and so they'll set the factor of safety. You'll say I want a factor of safety of whatever 1.5, and then they can, like Nathan was saying, so you would backtrack to find the radius to be able to determine the failure line or where the failure line would.
You can do that.
I mean, is that what they do, or is it?
Okay, again, that technique is used only for the software name flag. All other software is not plural form, right? All other software utilize the trial error approach. You assume this failure line and compute the factor of safety, then you assume another one, compute the factor of safety, assume another one, compute the factor of safety. The line with the lowest factor of safety will be the potential failure line.
So are they both doing the same thing, just in different ways?
Just different ways. Okay, that actually the technique used in flag is logical, but it's very unique one. I mean, my brain is already set to that kind of technique. And when I first learned about the flag, I thought, I cannot understand it because it was just the out of ordinary. But there's the technique. Okay, again, the key point is, if you consider dynamic effect, you can usually lower down the required factor of safety. And how do you know the required factor of safety? If you consider the dynamic effect, you've got to check your code. Typically, your code will say, okay, if you consider the dynamic effect, required factor of safety can be 1.1. If you did not consider it, required factor of safety is 1.5. But the thing is, okay, required factor of safety 1.1, if you consider the dynamic effect, that slope should be more reliable than the slope that has the factor of safety 1.5 without considering the dynamic effect.
So is the code, my main question is like, so is the code, do they base, I mean, to me it makes sense when you're trying to figure out what the factor of safety of something should be, that you should be basing it off of potential loss in that area if it fails. People and infrastructure.
Okay, your concept is correct, but we are not in that level yet.
Okay.
Nowadays, we are trying to implement potential loss of lives and properties in certain area. Then we may enhance the required factor of safety for certain structures. We are on the process of moving toward that direction, but we are not in that level yet.
Because wouldn't it be more economical to do that, or more costly?
That is called cost analysis. Okay. Again, is completely correct. You are right. We got to combine the cost analysis and the actual size of the structures. But we are not there yet. We are moving toward that direction. Any other questions? Okay, then I will see you Tuesday.